Chemistry students, this is to help you with solubility so that you can get a good start on your homework. And refer back to this if you need help with it when it comes time to study. So solubility is the most solute that can dissolve in a certain amount of solvent. Let's make sure we get those terms correct. So the solute is the substance that gets dissolved. The solvent is the material that is doing the dissolving. Generally, the solvent is the one in higher amount, the one that you have more of. So lots of everyday life examples for solubility. So let's think about this. If you are dissolving sugar in water, the water is the solvent. It's the thing that is going to do the dissolving, that's going to break apart the sugar solids and separate them out into separate molecules in the solution. The solute gets dissolved. So sugar water or salt water, water is the solvent. The sugar or the salt is the solute. It's the material that gets dissolved. Solubility of a material is the most that can dissolve. It's a maximum amount. We generally express it as grams of solute in 100 grams of solvent. And 95% of the time, that solvent is water. So grams of solute per 100 grams of water. It's just a ratio. If you had 200 grams of water, it would hold twice as many grams of solute. But when we graph solubility, it's always in grams of solute per 100 grams. We kind of scale it to 100 grams of water so that you have an even consistent comparison. So if you have an unsaturated solution compared to a saturated solution, unsaturated solution means it is not saturated. If you think about saturated, some kind of everyday life examples of the word saturated, if a sponge is saturated with water, that means it's full. It can't hold any more water. If a picture is saturated with color, that means it's full of color, right? So kind of think of it as full, saturated. An unsaturated solution is not saturated, it's not full. It contains less than the maximum amount of solute. So if you put more solute in, if you put more salt in your saltwater solution, it would dissolve. It's not full. That solution is not full of solute. It can hold more if it is an unsaturated solution. Whereas a saturated solution is one that is full. It is holding the most solute that it can possibly hold. If you put more in, if you put more solute in, it would just fall to the bottom because it's absolutely full. Again, think about this with salt water or sugar water. If you are adding sugar to a lemonade mix or something like that, powdered Kool-Aid, if you add more sugar, you put sugar in, stir it up, it dissolves. Put more sugar in, stir it up, it dissolves. If that's what you're doing, it's unsaturated. But if you put in more and more sugar, there will be a point where that lemonade cannot hold any more sugar. If you put more in, it's just going to fall down to the bottom. When you get to that point where if you add more solute, it just falls to the bottom, no matter how much you stir, then that's a saturated solution. It is full. It is full of sugar. It can't hold any more sugar. When you have a saturated solution, and you have solid material at the bottom, you have added more than it can hold. The extra just lays at the bottom. Then you have the third point on there. You have equal rates of the solid dissolving and then recrystallizing. This is another example of an equilibrium. The one that we've talked about before was vapor pressure, where something is happening in one direction and the other direction, and they're just happening at equal rates. So if you have solid material laying at the bottom of a saturated solution, the individual ions of that or molecules of that may be going out into the solution, but on the other hand, some of the ions or molecules that were in solution are going to hit that solid and kind of stick, if you want to think about it like that. Dissolving and crystallizing is happening at an equal rate. So again, comparing unsaturated and saturated solutions. The unsaturated solution on the left does have solute in it, in the solute. It is dissolved. It is not in a solid clump in the bottom. The saturated solution is full. There is solid material at the bottom. That water above that solid material, the solvent above that solid material, is absolutely holding as many solute particles as it can. So if you put more solid in that saturated solution, all you'd be doing is making a thicker layer of solid on the bottom. It cannot dissolve anymore. It cannot break any more apart. The water above it, the solution above it, is full in a saturated solution. Solubility is affected by temperature. So here's a graph of solubility versus temperature. First thing you always do when you look at a graph is see what the axes are. You have solubility in grams of solute per 100 grams of water versus temperature. You can see that for almost everything, for solid materials, increasing temperature increases solubility. We know this because of tea, right? So if you have room temperature water and you fill it up with sugar versus you have hot water and you fill it up with sugar, you're going to be able to get more sugar to dissolve in the hot water. For solid materials, solubility increases with temperature. For gases, however, it's the opposite. For a gas, it actually decreases as temperature increases. So let's make sure you can do the homework. That's what these examples are. So here's a certain temperature at 40 degrees Celsius. The solubility of potassium bromide is 80 grams per 100 grams of water. You need to identify whether they are saturated or unsaturated. So if the solubility is 80 grams per 100 grams of water, that means if I have 100 grams of water, it could hold 80 grams of potassium bromide. Anything less than that, no problem. Put it in, stir it up, it'll all dissolve. If I put in more than 80 grams into 100 grams of water, though, 80 grams dissolves and the rest just lays on the bottom. So our first example is, or part A, 60 grams in 100 grams of water. Well, 60 is less than that solubility, less than that maximum amount, so sure, no problem. Put 60 grams of potassium bromide in 100 grams of water, stir, it'll all dissolve. You will not be able to see any solid material laying on the bottom. 200 grams of potassium bromide added to 200 grams of water. What you need to do is scale it back to compare what would it be if it was 100 grams of water. Well, 100 grams of water is half of 200 grams of water. So 200 grams of potassium bromide and 200 grams of water would be the same as saying I put 100 grams of potassium bromide in 100 grams of water. 100 grams of potassium bromide and 100 grams of water is more than the 80 grams that 100 grams of water can hold. So that would be a saturated solution. If I did the situation in part B, if I executed that, I would have solid potassium bromide laying on the bottom of the beaker. 25 grams of potassium bromide in 50 grams of water. Again, we want to scale that to compare it to what it would be for 100 grams of water. So I'd have to double the 50 grams of water, so I'd have to double the 25 grams of potassium bromide. Example C would be just like having 50 grams of potassium bromide in 100 grams of water. That is below the solubility limit, so yes, that would all dissolve. Henry's law is referring to the solubility of gases in a liquid. What it says is that if I increase the partial pressure of a gas above the surface of a liquid, then that increases the solubility. It's directly related, so increasing the partial pressure of the gas increases its solubility. This is how they carbonate soda. They have very high pressure carbon dioxide gas above the surface of the liquid. That high pressure of carbon dioxide causes it to increase the solubility. Oh boy. There we go. And so more carbon dioxide dissolves. When you open the soda can, that releases the pressure, and that then decreases the solubility of carbon dioxide, and that's why you get the bubbles.